Today I'm going to tell you about how the body responds to the implantation of silk fibroin, a versatile implantable biomaterial that can be processed into many different forms, like fibres, films and scaffolds. It comes from the boiled cocoons of the silkworm, it has good biocompatibility and is readily available. It can be used to make tendons, vascular grafts and scaffolds for growing bone. Immediately after a biomaterial implantation comes the thromboinflammatory response. This happens in 3 steps: protein absorption, complement, and platelet adhesion. The first thing that happens is proteins present in the blood plasma bind to the silk. These plasma proteins have several functions. Vitronectin and fibronectin are attachment proteins that allow cells to bind to the material. C3 and IgG engage the innate immune system, and there are also some slow-release inflammatory factors. There is growing research that this provisional matrix has a significant role in the biocompatibility of materials, and by controlling what proteins absorb, the immune response can be tweaked. Silk fibroin, for example, is hydrophobic, which increases the number of plasma proteins that adhere to its surface. By adding a hydrophilic coating, it could be possible to reduce the immune reaction. Then, the complement system, part of the innate immune system, is activated. It's made up of 3 pathways: classical, alternative, and lectin. It works by cleaving a series of proteins that amplify the number of proteins each time, as well as releasing inflammatory molecules. So this is the inflammation. This is the amplification step here for alternative, and there's the amplification step there for classical. Next, it creates a membrane attack complex here. This membrane attack complex, if there was a pathogen, would poke holes in its plasma membrane. However, it can instead bind to the surrounding cells, overwhelming control proteins and lysing the cells. The inflammatory molecules released are responsible for attracting neutrophils and macrophages, inflammation, increasing permeability of capillaries, and marking materials for phagocytosis. Silk fibroin, in most forms, will engage the complement system. Silk films seem to engage the alternative pathway more than fibres. The alternative pathway activates due to the spontaneous cleaving of C3 into C3A and C3B, and the binding of C3B to silk, starting the cascade. Next comes coagulation. It's another protein cascade. It starts either from proteins from the damaged cells or from platelets. Its goal is to make thrombin, which is used to convert fibrogen into fibrin. The fibrin then binds platelets together. This will then bind to the surface of a biomaterial. If the shear rate is high, for example, with an area with high blood flow, they are more likely to adhere. The platelets then release cytokines that stimulate neutrophils and macrophages, which increases the inflammatory response. Silk has a low coagulation response with little platelet adhesion in vitro. This is why it's a good material to use as a vascular graft, as it is less likely to cause thrombosis, which is a blood clot in a vessel, than PTFE and PET. It's also got similar elasticity and strength to the vessels, reducing fluid flow disruption. The second step is acute inflammation. The first immune cells to arrive are neutrophils, attracted by chemokines released in the earlier steps. They come from the surrounding vasculature and, when bound to by chemokines, attach to endothelial cells and roll. They follow the chemokines from an area of low to high concentration to reach the implant. Once there, they attach to fibronectin and other absorbed proteins, The cells attached by focal adhesions. Integrin receptors on the cell binds to the RDG binding site on fibronectin. By expressing more receptors near to where the cell has bound and actin pulling the cell closer, the neutrophil flattens and tries to phagocytose the biomaterial. But as it's too big, it is unable. It also releases a cytokine called IL-8. This causes more neutrophils to activate as well as angiogenesis to occur, increasing the amount of blood vessels so immune cells can reach the implant faster. After a few hours, due to the large amounts of tissue damage and inflammatory signals, the neutrophils recruit macrophages. Macrophages are either seen as part of the chronic or acute inflammatory response, depending on the source, but most agree that they are the most important part of the immune response. Macrophages start out as monocytes in the blood. They then, like neutrophils, are attracted to the site of implantation, where they differentiate into macrophages. Macrophages also try to phagocytose the implant. There are two classes of macrophages. They often start as the M1 type that produce pro-inflammatory cytokines, but move towards the M2 type that promotes tissue remodeling. There isn't any good information on the ratio of M1 to M2 macrophages in silk, but from the mild immune response and the presence of fibroblasts, we can assume that the macrophages progress to M2. The foreign body response is the most severe inflammatory response to a biomaterial. Sometimes in response to silk, especially films and scaffolds, macrophages produce interleukin-13 and interleukin-4, which cause them to fuse into a multinuclear giant cell. So they go from one cell to join together to many cells like that. This allows them to phagocytose larger materials, and they also release reactive oxygen intermediates and proteases. This is usually considered as a failure, as the foreign body response can cause the formation of fibrotic capsule due to the production of ECM by myofibroblasts and implant failure. But in the case of silk scaffolds, it can be helpful as they break down the scaffolding, allowing ECM remodeling and cell seeding. For example, in silk vascular grafts, endothelial cells covered 90% of the surface of the lumen after 12 weeks, with collagen replacing some of the silk scaffold, transforming the graft into a more natural state, improving compatibility and reducing the risk of side effects. Macrophages also phagocytose the provisional ECM, removing it for the next step. Fibroblasts are the last step in the response to silk. They break down and lay new extracellular material around the biomaterial. The ECM is how cells are held together to make tissues and is made up of proteins like collagen and fibronectin. The new ECM integrates silk into the body and allows the cells from the surrounding tissue to bind. Silk is better than collagen at having a wound healing response from fibroblasts. There are possible adverse effects. Silk fibroin is a very biocompatible material with limited side effects. However, silk is made up of two proteins, fibroin and sericin. When these aren't separated, silk has a significant inflammatory response and is a possible allergen. This was most common in silk sutures made of virgin silk, popular in the 60s and 70s. When combined, virgin silk can cause a type 1 allergic reaction in some patients. This type of hypersensitivity is mediated by IgE and it causes the release of histamines from basophils and eosinophils. This can be very dangerous as histamines are systematic, meaning they spread through the entire body. Virgin silk has been known to cause asthma in children, and in the worst case it could develop into anaphylactic shock, which is potentially fatal. As we have seen, during the implantation of biomaterials, cells usually communicate by a multitude of cytokines, most of which are poorly understood. Cytokines are signaling molecules specific to the immune system. Signaling molecules rarely have only one function, and often in vitro findings don't correspond with in vivo findings. As well as that, most cytokines are unstable and rapidly degrade to modulate their response, making them difficult to study. When a cell releases a signal, it can be either autocrine, self-stimulating, paracrine, near-stimulating, endocrine, via the blood vessels, or contact-dependent. The first two are more common in biomaterial implantation. To stimulate a cell signaling molecule must bond to a receptor on the cell membrane. This causes the signal to be transduced by an intercellular signaling molecule. This then causes the cell to respond in a variety of ways. For example, releasing the contents of a vesicle, releasing a different signaling molecule, or migrating. We can also use signaling molecules, for example, by adding BMP2 to a silk scaffold. We can increase the number of cells that grow in the scaffold to make them differentiate into osteogenic cells, giving us artificial bone. Without adhering to a surface, mammalian cells won't proliferate. Cells attach either to the absorbed proteins on the surface of a cell or to the ECM made by fibroblasts after the immune response. I described the adhesion to absorbed proteins by neutrophils and macrophages with focal adhesions earlier. This is a better look at focal adhesions. They are also sensors. They transmit mechanical forces into the cell. These help determine cell orientation, shape, and differentiation. Cells attach to a protein called fibronectin in the ECM by focal adhesions, in the same way neutrophils do. Hemidesomes are another type of junction. They attach cells to a basement membrane with integrin receptors that connect to intermediate filaments in the cell. They provide strength and are common in epithelial cells. Cells are also connected to each other by cadaherns, which provide mechanical strength, as well as gap junctions that allow cells to communicate to each other directly. Testing may be the most important part of any biomaterial's life. A biomaterial needs to be tested to ensure it is safe and effective. Testing is a three-step process, going from a toxicological risk assessment to in vitro, or in a lab, and in vivo, or in an animal. The risk assessment looks for which chemicals in the device may be hazardous. Then, for in vivo testing, it's governed by a standard called ISO 10993. One of the most important tests is the MTT assay. It's used to determine the cytotoxicity, or how toxic the material is to cells. It works by growing cells on the material and then using a dye that only binds to active cells. This determines if the cells have grown. A genotoxicity evaluation finds out if the material damages genetic material. This to help prevent cancer or reproductive issues. They test this by exposing mammalian cells to the material and detecting chromosomal damage. To assess hemocompatibility or blood compatibility, materials are tested from thrombosis, coagulation, complement, platelet function, and red blood cell damage. In vivo testing is done on animals. Depending on where the material is implanted, determines which animal is used. This helps make the models more accurate. In vivo is necessary as interactions with the body are complex and hard to predict.